So I'm from Amazon, and Amazon is part of a suite of companies that you're all probably familiar with. So hands up in the audience if you've bought something from Amazon.com. It's pretty good. Okay, well, you all have the capability with that account to do big data in the cloud. But I'm not here to sell books, and if you've got a problem with your book order, Amazon.com is the place to go. So I'm from Amazon Web Services, and it's part of a family of businesses within Amazon.com. And because of that badge, we often get asked about how did Amazon get into cloud computing? How did we get from packing boxes to unpacking boxes and putting servers on racks? As I like to think about it. So a bit of the history. It's about 10 years ago, we started to enable a seller business, that third line of business within that first slide, where you could, as a seller of goods, sell your products and services through the Amazon e-commerce infrastructure, leverage the delivery network, leverage the website, the payment gateways, and so on. And part of that enablement made us get quite smart about how we did technology. Okay? We had to start handling large volumes of data. Our product sets grew. We had to handle higher transaction rates. We had to get smarter on the analytics we did around that data. And the technology teams had to get pretty clever about how they deployed stuff, because we started exposing what we did from an e-commerce basis to the outside world. And one of the things we did early on, I guess the original big data sharing problem, was our catalog. We enabled a web service that somebody could access over the internet for a business to search our book catalog and embed that search in their own website. And that's where this whole thing really started for us, because we then set a mission which was to enable developers and businesses to leverage the infrastructure of Amazon.com. Everything we do, from the data center through the software we run in that data center, that whole infrastructure play, enable businesses to build scalable, sophisticated applications. And the name Amazon Web Services really says it all, because everything we do is available across the web as a service. And I think that's what everyone now calls the cloud. Okay? Because of that, we've been doing big for quite a while. Right? So a nice little stat about the scale that we operate at is that in 2000, we were, or the stat around circa 2000, which Amazon was a $2.7 billion enterprise. And every day in the Amazon cloud on a global basis, the capacity required to run that business is provisioned in AWS. So that's businesses, hundreds of thousands of customers, from small startups to large enterprises, provisioning services within the cloud, and every day consuming the equivalent capacity of Amazon.com when it was a $3 billion business. And what we do keeps getting bigger. Okay, so one of the services we have is a service called Amazon S3, a simple storage solution. And it's a place where you can store objects, anything from 1 byte to 5 terabytes in size, and store it with an extremely high durability. We just don't lose data. You can choose the region around the globe that you store this thing, and you can always get it back. And people build websites on this. They build transactional archives on this platform. And recently, we surpassed 1 trillion objects in storage and 750,000 transactions a second reading and writing those objects. Okay, so that gives us quite a unique perspective on big data, okay? Because S3, if you like, is a big data platform that underpins many, many big data projects today. And part of that perspective comes from operating like a utility. So you heard about the utility providers and the open sharing of data just then from the previous speaker. But it's worth understanding what we think about utility computing and how we go about providing our services. And that sense circles back at how we see big data and how our customers use our services to do big data projects. So we see a utility like electricity. The things that you expect of electricity are it's on demand. Whenever you plug in, you can switch it on. You'll receive that electricity. You'll only pay for what you use. When you turn it off, you'll stop paying. That electricity is highly available. Every plug socket has some in, and that it's uniform. Okay, the electricity you receive is going to be consistent wherever you use it from. Utility computing is about taking infrastructure, the stuff that runs businesses today, modern e-commerce, modern data analytics, financial services organizations, academic institutions, the compute infrastructure behind those things, and making them available on exactly the same basis. So being able to use them on demand from a highly available basis wherever you are, pay as you go, only paying for what you use, and for a uniform capacity or compute or wherever you are around the globe. And what we've done is we've wrapped, essentially, the data center in this thing called an application programming interface. So everything that you can do in a traditional data center, you can do from a line of code on your developer's workbench. Whereas traditionally, you've got to get people to rack servers, plug networks in, provision software, and this can create a long time frame before you can actually start doing something in a computer environment. With Amazon Web Services, you can simply access all of the resources that you'd expect to be in a data center on demand through that API. And that is utility computing. So why did I talk about this? Well, there's two parts of that are relevant to big data. Okay? Storing data and doing computation on data. So two fundamental parts of the Amazon Web Services cloud. And we see that everyone's sort of big data problem is different depending upon the scale of data that you have. And the challenges start with big data at a relatively small volume. So you don't have to be somebody with thousands of petabytes of data to have to start thinking differently about how you handle your information. So from hundreds of gigabytes to thousands of petabytes, the challenges are pretty similar across the board. Our perspective of what big data is, it's when your data becomes so large that you need to start innovating about how you store that data, how you collect that data, how you analyze that data, how you share that data. Okay? And innovation's a key term, right? So everything that we do in Amazon Web Services, we like to think we innovate, and everything we've innovated around has been around a big problem, whether it be running the e-commerce infrastructure for Amazon.com, whether it be assisting genomics organizations to process the human genome. These are big problems, whether it be processing data or storing data. And we have a range of services that are included in there. I'm not going to give you a product pitch, but one of those later, EMR, I'll drop into to give you a real concrete example about how you can use services in AWS and how you can do so with a relatively low skill level and access some of the advantages that our customers do. You've probably heard different definitions of big data today, so it's worth also giving a nod to those. So on the left there, we talk about big data being very large volume with low density of information. So this might be Twitter streams, for example, where within those Twitter streams there are a few key pieces of information of value, but the rest of the time it's really not of interest to you as an organization. The 3 V's about data having high velocity, variety, and volume. I think IBM add a 4th to that, which is validity. And then on the right-hand side, the ubiquitous social network, so gathering network information from things like Facebook, where previously those things weren't available. Maybe 10 years ago, where we didn't have a wealth of social information to mine in order to incorporate into our business data. So there's many other definitions, but there are 3 common ones. We see unconstrained data growth, and we see this as Amazon because we're storing an awful lot of it, okay, for our customers. So zettabytes of data, 1.2 zettabytes in the digital universe, of the vast majority of that being unstructured data, whether that be video, whether that be unstructured text streams, and so on. And where does it all come from? Okay, so it comes from the obvious, so servers generating logs. It comes from the ubiquitous Twitter streams that I mentioned before. But we also have images generated from traffic cameras. We've got social graphs from Facebook and so on. Sensor data. So whereas previously we were unable maybe to collect data from remote sensors and smart meters, now we have the smart meters and we collect the data. And websites, the self-generation of Web 2.0, where users are generating content themselves, publishing it online. It's creating a universe of data that's growing and expanding ever more every day. So why is this happening now? Why are we getting this influx of data? Well, firstly, everyone's got a smartphone. Okay, so people are generating data on the fly everywhere they go, whether it be location data, whether it be tweets, whether it be status updates, and so on. More people are using mobile phones, and it's now easier to collect data in a machine-to-machine fashion as well, so smart sensors. There's more aspects to the data. There's greater variety of the types of information we're able to collect. We collect greater depth to it. We're collecting it on a higher frequency. We're doing it near real time. We're adding location to that data. That fantastic image of London from the Flickr photos just says a photo sharing site is actually generating a wealth of information around geolocation and able to map a city. And it's now possible to understand. So whereas previously we might have had to formulate very specific questions about what we wanted to get out of our data, it's now possible to experiment and to really understand data by asking many questions. Because we're able to put the compute resources behind crunching that data to get us the answers. So what's different? We collect more data today, there is more data to get, and data has gravity. Okay, so one of the key principles of big data from our perspective. So what does data having gravity mean? is that as your data grows, there's an increasing need to put the things that you do with that data close to it. It becomes unfeasible to start moving that data around when it gets to very large volumes. And it becomes a necessity to start publishing your applications next to data, and your data becoming the primary asset that you're dealing with. So cloud has the power to process data, and that's where the Amazon Web Services badge comes in, really. And a nice way of thinking about big data and compute and the relationship between them that's changing today is a nice little personal advert there. So when you have such large data sets, the treatment of that data, or the requirement to do something with it, is very fleeting. And you really need to be able to bring computing resource to answer a question, to do a search, to do a query to the data, and when you're done with asking that question, throw it away. So when I was in Germany, someone said that I'd spelt gosh wrong, but as I'm in the UK, I'm sure you will get it. And the idea being with an elastic cloud like Amazon is that you can bring one machine to bear on that data, or you can bring many thousands, and then you can turn them back off again when you're done. And back to that utility argument, you only pay for what you use in that process. So this is elastic computing in action. There's a nice little chart. So traditional data centers in the grey line, you have to provision some computers at a certain level to handle a particular need or demand. With elastic computing, when the blue lines hit, you can simply scale up and scale down the capacity that you brought to bear on that particular problem, whatever that problem may be, whether it be academia, whether it be complex reporting for financial services, whether it be consumer-orientated personalization of data to drive higher sales. And this is what I call the revolution. So we have data now, we're able to store it, we can analyze it, and we can do it economically. Okay? That's the revolution of big data, no matter whether you're talking 100 gigabytes or 1,000 petabytes, and you can do it fast. Okay? So thinking about it from a consumer angle, and obviously I am from Amazon Web Services and the family of Amazon, we're obviously a consumer company as well. So this is about asking questions like who your customer really is, based upon information that may be outside of your domain. What do your people really like? If you're engaging with customers over social networks, how do you get that information back into your planning cycles? What is happening socially with your products, and how do people really use your products? One of the interesting papers I read recently was from the CIO of Ford, talking about him collecting all information from his smart sensor connected cars to understand how people really were driving cars, so that he could design the next generation of products better. That, to him, was his big data problem. And before I came here, last night, I decided to have a look at how Amazon retail personalizes and uses big data to sell products to me. And I logged in, and I saw this slide, and I thought, that's an interesting set of recommendations been given me. So for those of you who can't see, I've got Moroccan oil treatment and some keratin shampoos. Okay, so I had a look in my inbox, and my inbox then, a couple of days after I think somebody had browsed on my account, I then got something in my shopping basket that had been placed in there but never bought, another bottle of shampoo. So I asked my girlfriend, is this yours? And she said, oh yes, I forgot to buy that. And she clicked buy, and she bought the shampoo. So there's some lessons here. Don't leave your Amazon account logged in at home, okay? And lesson 2, the more serious one, is use the data you have to drive proactive processes. So Amazon is using data about what I did in my account, where I clicked, where I went, to drive insight into maybe where my buying preferences are. And when I don't complete the transaction, it's following up with some proactive action, which has led to my girlfriend buying the shampoo. Okay. Another dynamic of that revolution, and it's back to that utility and elastic model that's interesting, is that an instance in Amazon is a computer, okay, and you can rent it by the hour. And you can have one instance for 100 hours, or you can have 100 instances for 1 hour. And on a small instance, a small computer, that will cost you $8. The price is the same, 100 for 1 hour or 1 for 100. So that brings in something you probably heard about today, which is Hadoop. Okay? And that's the logo for Hadoop. And we call that Amazon Elastic Mapreduce. Okay? So I'll skip over the product detail, but it's essentially a big computing cluster. So what is it? It's a framework that splits data up into little pieces and lets processing occur in parallel and lets you gather the results. Okay? Now, we wrap this Hadoop into a service to make it easy for you to consume. You don't need to have a high level of technical skill to use Elastic Mapreduce. You can focus on the analytics you want to do. So you can simply write some code and drop it into Elastic Mapreduce, and it'll get on with the job. And if you want to learn anything about these products, you can come and see us at the end. But it's about taking a very large, let's say, click log. So what did Amazon do around me is they were understanding what I was doing, the logs from the application servers, many, many petabytes or terabytes of data, and looking for lots of actions by John Smith inside lots of actions by everyone else. Okay. They were splitting the data into EMR, into many small pieces, thousands of pieces, and letting that process in parallel so that they could generate some aggregated results, the reduce part of the Mapreduce equation, to tell me what John Smith did. And because we parallelized that, we did that in a very fast time. So we're able to pre-generate some information based upon logs. So on a cycle, let's say an hourly or a daily cycle, crunching everything that's been going on and generating some data which then drives other processes. Now previously, that would have taken a long time to process, and you'd never have caught up with the volume of data that was being ingested. Today, with cloud computing and concepts like Elastic Mapreduce, you can actually process them in a timely fashion and get some insight out of it. So one instance for 100 hours, 100 instances for 1 hour, $8. 1,000 hours or 1,000 instances for 1 hour, $80. Okay? And the story goes on. So an example of that is a company called Yelp. And Yelp used that concept of processing data to pre-generate some information which drives, on a click of a mouse on a website, some real-time instant feeling results and personalization for their consumers. So they generate things like people who viewed this also viewed that. They'll look at review highlights, because this is a Yellow Pages type system in the States. Auto-completing as you type into a box, pre-generating things like that, top searches and adverts and so on. And they're running about 200 of these jobs a day on 3 terabytes of data to generate some information that would drive personalization, stuff that couldn't be done before. Razorfish is a company that use EMR, Elastic Mapreduce, and they've taken away the need for them to have people to manage these very large clusters of complex technology, to save them a load of time, and they were able to put out a load more adverts, and these were an internet advertising company as a result. So that creates innovation and agility. So one of the themes really around big data cloud is you don't have to be a technical expert to use it, and having big data shouldn't be a barrier to innovating around that data, because you have the capability to bring to bear technical resources to crunch a problem. So summarizing that, some of the rules that we have around building applications is one about simplifying your architecture of services. Don't install software and manage software. Use services in the cloud, because you can change this dynamic. You can spend most of your time focusing on what you do best, your business, not most of your time managing software and having very high IT bills. And Razorfish did that. They got a 500% increase on their return from their first spend. And bear in mind, they're doing 1.7 million targeted ads a day. You know, that would have been quite a big technical infrastructure they managed themselves prior to using AWS. Another social application that's out there is one called Shazam. You may or may not know it, but this is where you pin things of interest, and other people on their mobile phones can see it, so very geolocation aware, very social. They use some services, and to give you an idea of the scale, they're doing more than 1 million writes per second out of the EMR cluster. Okay, so they're processing data on a huge rate using cloud computing with no physical installation they've had to do themselves to make that happen. Another more fun example is a company called Playfish. So this is a company that does games inside Facebook. So you can play SimCity with your friends and things like this, or you could play Patience, card games. They have about 50 million unique users per month, and they're generating 500 million analytics events a day, about 2 terabytes of data. And they're using EMR and these techniques around processing big data to understand what works and what doesn't, because their users are very fleeting. They come, if they're interested, they stay, they might buy a game, otherwise they leave. And what they want to do is adjust everything they do on a daily basis to keep the money coming in from very casual gamers on mobile phones and Facebook. And they've never, ever owned a physical piece of equipment to do that. Now, on the sort of big data spectrum, it's always nice to put a really grand example out there of what you can achieve with big data in the cloud. so that you can get a sense of perspective and maybe put your problems or what you want to achieve on that sort of line and go for it, because it's not a big problem compared to some of the problems that maybe academia are tackling with this sort of stuff. So the cloud helps do the science that we are capable of. An example here of a 50,000 core supercomputer built by one of our partners on AWS running on the cloud. So what is 50,000 cores? I mean, this is 50,000 cores inside CPUs, and why does that matter? Well, the problem that they were trying to tackle was this one, which is a global problem, and it's the new cases of cancer that we see. Okay, so every day is crucial and costly when you're trying to find a cure for cancer. So crunching very large data sets and doing them in a faster way is obviously key to them achieving their goal. And the company they were working for was a company called Schrödinger, and they do computational chemistry, algorithms and design, and they're trying to solve the problem of identifying protein targets, the locks to cancer, and then the molecules that will fit on those, the keys, in many millions of keys. Okay, so a very, very large computational problem to solve. And they were trying to get a very high accuracy on their algorithm and screening about 21 million different combinations of compounds. So a big problem. They estimated that it would take 12.5 years of computation time to complete. Okay. They did it in 3 hours at $5,000 an hour thereabouts, instead of spending 20 million in infrastructure. Okay. So they created a 50,000 CPU supercomputer, ran it for 3 hours, solved their problem, turned it off and went home, and then redesigned the next problem set that they wanted to pass through it, rather than spending a year building a data center and unpacking all those cardboard boxes and installing all the servers. So cloud enables big data collection, so takeaways from today. You're able to get data into the cloud, and incidentally, even if you think that the bandwidth that you need to push your data in there doesn't exist today, you can always put hard drives and tapes into cardboard boxes with Amazon, ship them to us, and we'll plug them in and make your data available into the cloud. So that's a blocker for anything you're doing. You can very easily get a very high bandwidth truck, a FedEx box, and stick that over to Welters. It enables big data processing. So back to the idea of bringing compute to your data, creating very large compute arrays, solving very difficult computational problems, and then throwing it away and doing it very cheaply. And lastly, collaboration. So once you have data in the cloud, and you can have control over that data, you can collaborate and share on that information. So whether that be for business processes, or whether that be for other reasons. So some of the examples of public data sets that we make available are 1,000 Genomes project that you may or may not have heard of. So a deep catalogue of 1,000 people's genetic information being added to all the time with their medical history, their records, what's going on in their health, their daily lives, for medical institutions and academics to read, to process, and then publish their results back into an ever-growing data set. And there's examples like that for Amazon where we do that publicly, but also communities on Amazon sharing the information between themselves. It's possible because it's in that cloud basis. It's on that technical platform that allows everyone to access it across the internet. So if you want to have a play, even if you just want to put your internal personal blog up, you can have a go and sign up at amazon.aws.com.